So let's just get on the same page. Today's the 13th. So what we need to know is, so here's our goal. Solve the Hodgkin's or Hodgkin-Huxley equations. Now the problem with these equations is there's 4 of them, and they're 4 differential equations, and you can't solve it by hand. It can't be solved using symbolics, you know, what we call analytic solutions. It's too difficult. So I know we don't talk much about this thing, but they're non-linear equations, which if you want to, anytime you hear the word linear, you can maybe think easy. It's not necessarily true. And then if you hear non-linear, you think hard. So these are hard equations, but remember, we want to make that picture of the voltage potential. We want to get that. That's our goal. And so what I wanted to do is I wanted to give you some practice. Instead of solving 4 equations simultaneously, I'm asking you to solve 2 equations in 2 unknowns. And I gave you 2 basic examples. I actually gave you ones that you could solve by hand. These are very simple. I don't want to say simple. I'm using simple in a relative meaning. Like, it's not simple for most humans. You have to take some time to learn this. But relative to these crazy the Hodgkin-Huxley equations, these are simple. So, and they're also simple in the sense that you can solve them by hand. And what's nice about that is, since we can solve them by hand, now I'm not asking you to do that. I'm telling you what the solutions are. I solved them by hand. I'm telling you just to verify that they're solutions. So let me explain what that means in a second, in case you're not sure. So the part A in both problems is you're going to do that by hand. It's just computing some derivatives and plugging them into the equations to see that it checks. That's what it means to be a solution. And since we can solve these easy ones by hand, what we can then do is we can go to Octave and then solve them using Euler's method. And then we can compare our actual solutions that we found, the exact ones, with the approximated solutions that the computer finds. So, so this is our goal, and I want to just walk us through this. So to achieve this goal, we practice with what I would call baby problems. And that's, you know, that's not offensive. I'm not calling you guys babies, but this is how you learn. You start with the easy things, and then you build your way up to these more difficult things. So let's just work through this. And then we'll see what I mean. So let's start with, this is going to be for the homework problem. So I have an example. I have x prime. So x is a function. And if you look at the context, well, let's assume the independent variable's t. So I have 2 unknown functions, x and y, and they're related in this relationship. And then I'm given 2 initial conditions. So I'm given that x, when I plug in 0 in x, it gives me 0. When I plug in 0 to y, it gives me 2. So here's my claim. My claim is that x of t, which is e to the 3t minus e to the negative t, and then y of t. So in order to be a solution, we need a pair. We need an x and a y, because there's 2 unknowns, x and y. So in order for it to be a solution, then this guy, this is my claim. So when we say verify, what we mean is let's plug these functions into this system up top and make sure that it works out. So go back to when you first learned algebra. One of the first things you did with equations, most likely, is the teacher said, show that this number as a solution. So what you would do is you would plug in the number and show that the equation was true. And then when you first learned how to solve equations, your teacher would always ask you to check, plug your solution in and make sure it checks, right? So that's what we're doing here. So the one way to do this is I am going to note that what is x prime? Well, x prime of my function is, if I take the derivative, it's 3e to the 3t plus e to the negative t. And what's y prime? Y prime is 3e to the 3t minus e to the negative t. Those are just the derivatives of the solutions that I gave you. So now what I want to do is I want to verify that this guy right here, so let's use a different color. I want to verify that this guy is equal to x plus 2y. And I want to verify that this guy, the purple guy, is equal to 2x plus y. That's what I need to do. So does x prime equal x plus 2y? That's what we want to check. Well, let's plug it in. Well, x plus 2y, what does it equal? Well, it equals x, which is not 3. It's, what's x? X by definition, or what we told you, is 3t minus e to the negative t plus 2 times y. Well, what's y? Y is e to the 3t plus e to the negative t. So if I combine my like terms, I have e3t minus e to the negative t plus 2 e to the 3t plus 2e to the negative t. Now, if I combine my like terms, this gives me 3e to the 3t, and then negative 1 plus 2 is plus e to the negative t. So it does indeed check. So I verified the top equation is valid. And then similarly, you can verify the bottom. Do you guys have any questions about that?
Wait, so we don't need octave for this question?
Or not for 1A, not for part A.
Oh, okay.
Part A is just a hand calculation. Now, the point to remember is, for most systems of equations, you can't even do part A because it's impossible to find the actual precise solution by hand. Does that make sense? So part A only works in these problems because they're quote unquote baby problems that we can solve without a computer. Okay, now, so let's say this. So in a similar manner, and I'm not going to go through it, you should do it for yourself. Okay, so for part B, now we need octave. So let me switch screens. Which one is it on? I gotta show screen too. So right now, do you guys see octave?
Yeah.
So if I go to documents, I gotta go to my octave folder. I gotta make sure remember up here in the left. And what I'm gonna do is I'm gonna go to my editor, and I have to open up my foul. So which one, what did I call this one? I loaded it for you guys. Where's it at? It is. It's Euler 2x2. This is the foul. So I wrote this for you guys last week, and this is, you can find this foul on, what is it? You can find it on, I'm losing my mind, Canvas. All right, so what I did is I modified it slightly. I tried to give you some commented code. That's the green stuff that explains what I'm doing. And then I already programmed this one to solve it. So if you look at this, if you look at what I'm doing is, instead of having this to type the equations in for every separate problem, all you're going to have to do at the top is type them in. So look at my f. My f is, if you read this, it's x plus 2y. Well, that's what my right-hand side is over here. And then what's my right-hand side for the second equation? It's 2 times x plus y. So you'll see that right here. So remember, this is how we define a function in Octave. The first thing we do is tell you what the rule is, and then we give you the variables. Okay, then I have to tell it what my initial conditions are. So I pick a step size. So let's say 0.01. And then let's say we're going to run some iterations, maybe 10, maybe 100. So if I want to do 10, let's say 10. And then I have my initial conditions. Well, what's my very first time? My very first time is t1. What's my very first time? It's 0. Now you might say, why is it 0? Well, look at the equation, or if you look at the homework assignment, what is our initial conditions? We tell you what x is at 0, and we tell you what y is at 0. And so that means that your first time is 0. If I told you what x and y were at 1, your first time would be 1. Okay, once I tell you the initial conditions, then I just compute all the approximations using Euler's formula. So if you look at what I have written here, this is just a generic form of Euler's scheme. And it looks very overwhelming when you look at the code on the computer. So it's going to take some time for you to get this. And as I said, it's very unfortunate. If this were a normal class, we'd be sitting in a lab right now. You would be typing, I would be looking over your shoulder, I'd be answering questions, but it's just, we can't do that right now. It's impossible. So we're trying to make the best of it. So, So anyhow, what this does, what this for loop does, is this for loop computes all the approximating x and y values. And so then what we want to do is we want to graph them next to their actual values, which, because this is a simple system, I can tell you what the x's and the y's are. I know this solution. I know what it is. Now, notice that I'm using TT. Well, because I don't want to use T again, because I already used T for another variable. And if I write X here instead of XX, it's going to confuse what X is. So I have to come up with a new name. So I just came with XX and then YY. And then down below, I'm going to plot 4 things. I'm going to plot my approximated solutions, there's 2 of them, and I'm going to approximate my exact solutions. And so this thing that says hold on, all that does is that just tells you to keep each one of those functions graphed. So watch what happens when I run this. When I run this, I'm going to get a picture. It's going to take a few seconds the first time. So we wait. Have a sip of your water. Sing a song. Think about life. So it'll take a few moments for the very first time. After this, it won't take long. So what you'll see is, you'll see that, in fact, the dotted lines, if you look at my code, the dotted lines, and hopefully you can learn by context. See these 2 dashes here? These 2 dashes tell you to dot the line. So the dotted lines are the approximations, and the solid lines are the exact solutions. So since we're not going very far, we're only doing 10 steps, we don't see any air at all. It really doesn't look like air. Now, maybe if I zoom in, now I see that there's definitely some air. The actual curve is orange. That's the exact solution. And the approximated solution is dotted. Okay, so let's see. That kind of looked boring because we only did 10 steps. We didn't go very far. What if we go out to, say, 100, though? We go out to 100 and run it. You'll see, okay, look, these are definitely look like exponential curves, which we expect. Look at our solutions. So maybe you zoom in on this and see what's happening up here, and you see, okay, there's definitely some air. The orange and black are the exact solutions, and the blue and red that are dotted are the approximated solutions. So I'll delete it and run it again just so you can see. These are clearly exponential curves. Well, maybe not clearly. And here's another thing. Look at both of these. Look over here on the x-axis. Look at the black curve. Where does it go? It starts at 0, 0. Like we expect. Look at the initial conditions. For x, it's x of 0 is 0. And then this guy, look where it starts. It's at 0, 2. So if I zoom in over here, notice it starts at 0, 2, and this guy starts at 0, 0, as we expect it to. You guys have any questions about this? I think maybe since we're not in a classroom, the best thing for you guys to do is to try to do it on your own. And then if you get stuck, schedule a Zoom meeting and we can work on it together. We could, you know, I think you'd be able to share your screen if you wanted to. Now, just for fun, what happens if we go out to 1,000 instead? Well, now that's kind of like really seeing the exponential behavior. Look at that. Ooh, this thing blows up real quick. So maybe instead of 1,000, if I go to like, say, 250. There you go. So now you look, you can clearly see we're dealing with some exponential behavior here. You guys have any questions about this?
Yeah, what does figure 1 mean, like on line 43?
I'm just naming the figure.
Oh,
This
okay.
just gives you a simple way if you wanted to save it. So here's a nice thing. You can actually tell it to save it to like any type of file you wanted. And so like when later on, and you'll do this in your other classes for sure, Abdul, especially when you get in like engineering courses, what you'll do is you'll write figure 1, then you'll have figure 2, figure 3, and then you can refer to them. So you can just write save figure 1 and then give it a name. Maybe you call it, you know, solution 1, and then you can save it to any type of file you want, PDF, EPS, JPEG. So you're going to learn a lot of that stuff in other classes, but that's a good question. And notice I got rid of the axis, but if you wanted to play around with it, you could change your axes. Notice I commented it out. So you can, if you wanted, you could play around with the axes so that you see the picture in a different light. Does that make sense?
Yep.
Now, again, I really would encourage you to practice with these simple ones because I showed you this before. If I go back to my Hodgkins-Huxley code, look how involved all these equations are. But if I run this, 7 years later, see, I get, this is what we want you guys to get. It takes 4 equations to get this voltage picture we want. You guys have any questions about this? Comments? And look, don't get stressed if you can't get it right away, and even if you can't ever totally get it. This is hard stuff to learn, and it's really hard to learn when we can't sit in the same room together. But I did want to share the code with you, and if you play around with it and you have questions, like you might have a question like, what does this mean here? Like why, notice like you know, this could be very confusing. Why am I calling t of 1, h t of n? Well, this means that my variable TT is going to have the same starting and end pointing as T does. So if I were to come up here and change my problem, maybe my initial conditions were different. So really, when you want to change the problem, the only thing you guys have to change are the functions f and g, and then your initial conditions. That's it. You don't have to touch anything else. Well, okay, down here you have to modify the exact solutions. So you only need to touch three things: f, g, the initial conditions, and then XX and YY. Other than that, you don't have to touch anything. Now, of course, you're more than welcome to do whatever you want to this code to learn from it. And that's how you learn. You really do. You learn by playing with other people's code. That's just how it is. Questions, comments? Now, again, I'm not going to expect you to write your own Hodgkins-Huxley code either. I'm going to give it to you, but I'm trying to build up. So if you're only going to get out of this what you put into it. So if you spend time with this, even if you fail and you don't get it the way you want to get it, or you feel like you should be getting it, that's okay. You're still learning something. You guys have any questions? Comments? Well, if you guys don't have questions, then what I think you should do is I think you should try to work on this. And if you do get stuck or have comments or questions, email me or we can set up a meeting and talk about it. Because the next homework's going to be, I'll give you the Hodgkins-Huxley code and ask you to reproduce it. And then we'll do some more math after that. We'll go back to actually doing computation on Wednesday. You guys have any questions or comments, even if it's not necessarily about this? Going once, going twice. All right, well then I say thank you, and then try to work on this now. That way if you have questions, it's fresh in your mind and you can ask me. All right. Okay, then I say, all right, well then that will be my advice to you. And then Wednesday we'll start doing some more, we'll actually do some more calculation type stuff. And then we'll go from there. So you have a question, Abdullah?
No.
Okay. All right, well then please work on this. And then if you have questions, let me know and we'll go from there. And then Wednesday we'll talk more about the Hodgkin-Huxley and we'll do some math and hopefully it'll be fun. And I will talk to you guys then. All right. All right, guys, take care. Thank you very much.